Okay, so we still have a couple of minutes. If anyone has questions, this is a good time to ask questions. Otherwise, I'm gonna just kind of wait out the clock until just trying to give people a chance to get in here. I'll turn my notifications on for a little bit. If it gets to be distracting, I will turn it off. Here. Okay, so we still got about another minute. Ho, ho, ho. Okay, let me see. So welcome, scholars. So we're going to wrap up the week. We have two sections that we're trying to get through today. Let's see. Let me see. So our goal is to get to 3.3 and 3.4. 3.3 is on graph sketching, asymptotes, and rational functions. No real announcements. Just as long as you're kind of making your way through the assignments in my open math. My open math. Sorry, not my open math. My math lab. Unlimited attempts. I think for you all, it's unlimited attempts and only a 5% late penalty. So you pretty much have until the end of the semester to get everything in. I'll be updating grades soon after, since I know we recently finished exam one not that long ago. So, yeah, I'll be updating them soon, probably. Yeah, so yeah, let's just kind of keep moving forward. As usual, if you have questions, feel free to unmute yourself and we can talk about it. Hopefully, you all have been getting my notifications. I've had a few students I've been going back with a few students from a couple of different courses. I know a few of them were for here, and so if I feel like if I can answer the question in a YouTube short, I usually post it. So it is a good idea to be subscribed to my YouTube with your notifications turned on, so that when I do these posts, you can at least, even if you don't watch it, at least you can kind of be aware. And like I feel like, again, if I can answer it in a short, because I know the nature of things in this day and age, the shorter the better. So if I can answer the question in a short, I will. If I feel like I need more time than a short, or if I'm like sitting down and like actually going to write it out, then I'll make a longer video. And yeah, so like as you all start making use of the Ask My Instructor, I just load it to my device and I try to answer it as succinctly as possible. Sometimes I give the answer, sometimes I don't. Right. And if you need me to go further, I can. Okay. So let me see. Last time, I think we introduced. Let's see. So like because of like people trickling in like this is why notification turned off, because it's like really distracting for me. But it's okay. It's okay for right now. So last time we introduced applications of the derivative, right? So the whole time we've essentially been talking about the derivative, And let me see. I think with section 3.1, we explored the first derivative test and the information that gives us. The first derivative tells us whether the original function is increasing or decreasing. When the first derivative is positive, that means the original function is increasing over the given interval. When the first derivative is negative, the original function is decreasing over the interval, right? And then so we use the first derivative test to like identify local max and local min, right? Whenever the function went from increasing to decreasing, right, then we would have a local max. If it went from decreasing to increasing, we had a local min. And then in section 3.2, we took it a step further and we were looking, okay, what does the second derivative tell us about the original function? The first derivative tells us increasing or decreasing or constant. The second derivative tells us concavity, right? So which way is the curve opening? If the second derivative is positive, the original function is concave up. So it's like a cup that's opening upward. If the second derivative is negative, the original function is concave down, which is like a cup opening downward, right? So we kind of combine the first derivative test with the second derivative test. If we have our critical value from the first derivative test, and then if that critical, once we look at the second derivative, if it's positive, that means the original function is concave up, which means we should have a minimum there, right? When we plug in that critical value into the second derivative and it's negative, that means the original function is concave down and we should have a maximum, right? Sometimes either we can't use the second derivative test, then we just go back to the first derivative test. All right, so that's a recap of the first two. Let me let the student in. Right here. Okay, I think we're good. Let's keep going. Now, I guess there is a way I can do that a little bit faster. Yeah, let me try it out. I'll go ahead and get this student. I'll just let him in. Okay. So I think if I go like this, put that there, and I think we're good. I'm gonna just suppress it. It should work. Okay. So we've talked about the first derivative test, increasing or decreasing. Second derivative test tells us about concavity, and then where the second derivative goes from positive to negative or vice versa, that's gonna be called a point of inflection. And so you find a point of inflection by first you find the critical values of the second derivative. Basically, when you have the second derivative, that's the critical value is going to occur when either the second derivative is either 0 or undefined. And then, see, that's what I was looking for. Let me turn this off because that's the one. Oh, see, I forgot my shortcut. I still don't know who this is. I'm gonna let him in for now. Let me see the time. I'll probably let it ride until I see the time is 6:15, and then I'll suppress the audio. So someone just joined. It says Zoom user. You should definitely update your display name so it shows your student name. Right now, I haven't given you attendance credit because I don't know who you are. So you should send me a DM, a direct message, identifying yourself. Okay. Let's see. There we go. It's actually kind of working. Right here. Okay. So there is one person on the call right now. I just don't know who you are because it didn't show your name. Okay. So let's go a little bit further, right? So now let's move into section 3.3, graph sketching, asymptotes, and rational functions. So let me give a little synopsis of this. I actually started to go into some of the techniques here, and I think I'd rather just summarize it first before we kind of get into some of the jargon. So when it comes to graphing rational functions, there's an approximate 6-step procedure that I personally like to do, right? It is a little bit, I'm giving you fair warning. These questions can be long. It can be a little bit involved, but if you just kind of like slow it down and just take it step by step, part by part, do the best you can on each part. If any part is giving you trouble, just put a pin in it, skip it, and go on to the next part. That actually served me in like previous examples. So if I were to summarize sketching rational functions, that's where we have a variable in the denominator. The first thing I like to find are my intercepts. So that's like 2 of them. I usually like to start with the y-intercept, find that, and then do my best with the x-intercept. And And then from the x-intercept, I like to explore any asymptotes. I think we talked about at least two. Give me a moment. Okay, I'm getting the flow now. We've talked about at least a couple of different ways of exploring asymptotes. You got vertical asymptotes, horizontal. There might be no asymptotes, and then there's also like oblique or slant asymptotes. So maybe that'll come up and we'll talk about it more. So we talked about intercepts, asymptotes. Another good thing to test for is do a test for symmetry, right? So determine if the function is even or odd, and we'll explore that in just a moment. Let me see if there's something else. Oh, we can also do first derivative test, second derivative test, right? So that's like 4 or 5 steps right there. We said intercepts, asymptotes, symmetry, our first and second derivative tests, and that's loaded. And then a few additional points between and beyond your critical values, or just a few additional points. I used to do between and beyond. What's the time? I got 6 more minutes. I used to do between and beyond my critical values and x-intercepts and asymptotes. I guess we could do that. So a few additional points. We'll explore that in just a moment, and then we put all that together. Let's summarize that one more time real quick. So when I'm graphing rational functions, the things that I'm looking for, I do my intercepts, so x and y. I usually do y first. We can explore asymptotes, right? So vertical asymptotes, horizontal asymptotes, any slant or oblique asymptotes. We can do a test for symmetry. We can do our first derivative test, second derivative test. I kind of group those together. A few additional points, and then put it all together, right? So it is a mouthful, but if you kind of slow it down and take your time and take it piece by piece, it's not as bad as it seems, right? So, I'm just trying to but ease you guys into this, because a lot of times this intimidates students, but it's really not that bad. You know how to do all those different parts. You just got to be able to put them together, right? One quote I saw said, there's no such thing as complex. What we consider to be complex is just a long string of simple ideas. I think if I talked about any of those ideas individually, I think you guys can handle it. So the rational functions is just putting all those simple ideas together, right? You got to slow down. It does take a little while, but it's doable. Okay, so that's my summary of this section. So let's look at we have some objectives here. 1, find limits involving infinity. 2, determine the asymptotes of a function's graph. And then 3, graph rational functions. Okay, so let's see. And it's a rather long section, so we'll do the best that we can. A rational function is a function f that can be described by, we have some polynomial p of x over some other polynomial q of x. Where p and q are polynomials, where q is not the zero polynomial, because we cannot divide by 0, right? The domain of f consists of all inputs of x for where the denominator function is not 0. So if we have any x values that makes the denominator 0, we have to throw them out. Otherwise, the domain is going to be all reals, again, except any x that makes the denominator 0. So the line x equals a is going to be a vertical asymptote if any of the following statements are true. The limit as x approaches a from the left of f of x goes to infinity. The limit as x approaches a from the left f of x approaches negative infinity. The limit as x approaches a from the right approaches infinity, or the limit as x approaches a from the right approaches negative infinity. So this is talking about in a graphical sense. If you're looking at the graph, and as x gets closer and closer to some number, if your y values tend to either positive or negative infinity, then we'll have a vertical asymptote. The graph of a rational function never crosses the vertical asymptote. If the expression that defines the rational function is simplified, meaning that it has no common factors other than -1 or 1, then if a is an input that makes the denominator 0, the line x equals a is a vertical asymptote. So in summary, when we're working with rational functions, the vertical asymptote is going to occur whenever you have, if you're evaluating, whenever you have a result that's give you some k over 0, right? If you have some number over 0, that's going to give you a vertical asymptote, versus if you evaluate it at a candidate and it gives you 0 over 0, that's going to be a hole or a gap in the graph, not necessarily a vertical asymptote. Right. So again, it's kind of a mouthful, but I feel like it'll flow a few examples. Okay, so in this example, determine the vertical asymptote of the function. Notice that nothing cancels. So the vertical asymptote is going to occur, actually something does cancel. Normally the vertical asymptote occurs at any x that makes the denominator 0, provided that x does not also make the numerator 0, all right? So if it's already in completely factored form, so you should be able to quickly determine what values of x make the denominator 0, right? So if we just want the vertical asymptotes, we should simplify it. Like, if we set the denominator to 0 and solve, from the first factor, we get x equals 0. From the second factor, we get x equals 1. And the third one, we get x equals -1, right? But notice this x is canceled by this guy. So this guy is not a vertical asymptote. This one is actually a hole in the graph, right? And so these two are vertical asymptotes, this one and this one, right? All right. Let me see. Let me kind of mention this. So like, when is a function equal to 0? 0 divided by some number, this is okay. All right, this is okay. So this is going to be equal to 0, right? So 0 divided by some number is okay. That's going to be equal to 0. But some number divided by 0, that's a KO. So you want to knock that out. So this is going to be undefined. Undefined, right? And then if a number gives us 0 over 0, this is a hole in the graph. This is a hole / gap in the graph, right? So 0 over some number, that's okay. That's going to be equal to 0. Some number over 0, that's a KO. So that's going to be undefined. And so that one, this one here, this describes our vertical asymptotes. So the KO scenario, that describes our vertical asymptotes. Notice when we plug in 1, I think we get -1 over 0. So that's a vertical asymptote. When we plug in -1, plug in 0, we get 0 over 0. So that's a hole or a gap in the graph. So it only asks us to find the vertical asymptotes. So that actually occurs for ±1. Okay. So that should have been a little bit of a review, but I was just trying to remind you all of that if you didn't already know it. Copy. Okay, let's see, how do we do? Since ±1 make the denominator 0, these are the vertical asymptotes. And so what the text did, they simplified the expression first. If you simplify this, cancel. And then if you find the values of x that make the denominator 0, those are going to be your vertical asymptotes, right? Okay, as usual, if anything is not clear, feel free to unmute yourself to get my attention and we can talk about it.
Excuse me.
Yes.
I was wondering if my name wasn't popping up originally. I was wondering if you had marked me present.
What's your first? What's your last name? I can't hear you.
Marcus Henderson, Marcus, and then Henderson.
Yeah, just when you get a chance, just update your Zoom name so that way when you log in, you'll get it automatically. There may have been another class where that happened as well. I tried to get your attention, but I didn't know who you were. So it shouldn't be an issue. I'm just saying,
Name is.
Yeah. Okay. Yeah, I got you. Okay. All right, so let's keep going. Quick checks I leave as an exercise. So then we have the line y equals b is a horizontal asymptote if either or both of the following statements are true. So again, this is in a pictorial representation. As x goes to positive infinity, then our y tends to some number. Or if as x goes to negative infinity, y tends to some number, then that means we're going to have a horizontal asymptote. With the vertical asymptotes, we never cross them, right? It just kind of like pops up on the other side. With the horizontal asymptotes, we can cross them, but we're talking about how the function behaves as x tends to either positive or negative infinity, right? So as x goes to one extreme, is our y tending to some number, right? If it is, then we're going to have some horizontal asymptote of y equals whatever that number is. Now, there is a three-prong test. I'm not sure if we've talked about it or not. I know there's a couple of different ways to kind of go about this. The graph of a rational function may or may not cross a horizontal asymptote. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. The degree of a polynomial in one variable is the highest power of that variable, right? So to find the horizontal asymptote, we compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less than or equal to the degree of the denominator, then we're going to have a horizontal asymptote. Otherwise, we won't have one. We might have some other kind of asymptote, but it won't be horizontal. Okay, let's see what else we got. So determine the horizontal asymptote of this function. Okay, so I think that the technique that they're using here, so in order to find, if we're concerned with the horizontal asymptote, let's consider what happens to this function as x tends to positive infinity, right? So what we're going to do, let's factor out x squared. Let's factor out x squared from all the terms, right? So then f of x equals, now if we factor out x squared from everything, on top, we're going to be left with what? 3 plus 2 over x minus 4 over x squared, right? That's if we factor out x squared from all the terms on top. And let's do the same thing on the bottom. 2 minus 1 over x plus 1 over x squared, right? So now what we want to do is consider the, let me see. We want to let the absolute value of x get really large, like go to infinity. So we'll say something like, let the absolute value of x tend to infinity, right? So we want to see what happens as the absolute value of x gets really, really large, right? So let's start with this guy here, right? Let's just focus on this term. So for instance, we're going to let x go to infinity. Let's start with when x is 1, what's the result there? If we just focus on just this red part, right? When x is 1, we get 1. When x is 2, we get a half. When x is 10, we get 1 over 10. X is 1,000, 1 over 1,000. When x is 1,000,000, 1 over that numerator being fixed, and that denominator get a really, really large number, what number is that really close to? As that denominator gets bigger and bigger and bigger, this guy gets closer and closer and closer to what number? Can anybody answer that? If the numerator stays fixed, say we have 1 over 1,000,000, what is that really close to? What number? If we have 1 over 1, what's that number? What's that result? What's 1 over 1? Okay, I think you guys are MIA. So I'm just going to say it, and that might be a little bit worse. It would be better if I can get a little bit of back and forth. But if I just say it, I don't know if you're going to see it, right? So when you have a fixed number over a really large number, this tends to infinity. This tends to 0. And then once you get the concept of that guy, this guy behaves the same way, this guy behaves the same way, this guy behaves the same way. So as the absolute value of x gets really large, all of those guys tend to 0. And then all we're going to be left with, and then actually, I guess we can do this as well. These are going to cancel. And all we're going to be left with is 3 over 2. All right. So as the absolute value of x tends to infinity, all those terms get closer and closer to 0. So they essentially just like dissolve out. And then a number divided by itself is 1. And the only thing that's left is 3 over 2.
All right? Excuse me, Professor.
Uh-huh.
In the portion where we cross out like the 2 over x and the 4 over x squared, when we're crossing those out, making those 0, we're crossing those out like based off of the denominators below them.
Yeah. If you have a fixed number over a really, really large number, a denominator is getting bigger and bigger and bigger, then that term itself is getting closer and closer and closer to 0.
Okay.
Right. So like that's why I was trying to like lead you guys into it. Like with this first one, when x is 1, then 1/1 is 1, right? When x is 2, then it's a half. When x is 4, then it's a quarter, and then you can go like an eighth, a 16th. Notice as that denominator is getting bigger and bigger and bigger, that fraction is getting closer and closer and closer
to 0.
It's getting smaller, right? Yeah, it's getting closer to 0. So whenever you have a fixed number over a really, really large number, all of those terms essentially go to 0, right?
Okay.
And then with these guys remaining, a number divided by itself is 1. So with this type of expression, the only thing that's left are these guys.
Okay.
Yeah. It's a little bit trippy, and that's about the best I can do to articulate that. It's a little bit trippy, but it makes sense, right?
Yeah, I got you.
So, you just have to kind of like let it process. Let me see.
Sorry.
Yeah, you good. You good. Let me get the student. I think that might be him. Okay, right. So with this example, one thing I want you to notice also is that the degree of the numerator was equal to the degree of the denominator. So then the horizontal asymptote occurred at the ratio of the leading coefficients, right? And we had this little procedure. Let's see what the text says. Let's see how the text goes about it. Okay, so we have a copy of the. What's the time? Okay, let me suppress that because it's distracting. It was fun while it lasted. Let's go here. Ooh, he's here. Okay, I got him already. And I'm sure it's probably just people changing devices, but it just distracts me. Let's go here. Let me see. Yeah, I got you. Okay, so we're looking good. Let me mark everybody else's absent. Yeah. Okay, not bad. Not bad at all. Okay, and if they show up, I'll look at it. So let's see how the text did it. So they had a copy of the original. They said first divide the numerator and the denominator by x squared. So yeah, we factored out the x squared. We kind of canceled it a little bit late, but we essentially did the same thing. We got a result like this. Then now find the limit as the absolute value of x goes to infinity, or it gets larger and larger and larger, right? And then so we did it for x going to positive infinity. You can make a similar argument for x going to negative infinity. As long as you get the concept behind those terms canceling out as x goes to infinity, it's a similar argument for the absolute value as x tends to negative infinity. So then you saw how all of these guys went to 0, right? We did that exercise together, and the only thing that was left was the 3/2 in either case, right? So therefore the line y equals 3/2 is going to be a horizontal asymptote. So as our function goes far to the right or far to the left, our y value is going to get closer and closer and closer to 3/2. Okay, that was I think that was interesting, right? Okay, so that was exploring horizontal asymptotes. Let's see. So we've explored vertical asymptotes. We did a good amount. Now, horizontal asymptotes to me, like in college algebra, we kind of articulated a little bit different. It was a 3-prong test, but it was essentially the same thing. I think I'm gonna just leave it the way that we have it, because I think that's enough. I don't want to give too much. So we've explored vertical asymptotes, horizontal, but then we said that the horizontal asymptote is going to occur as long as the degree of the numerator is less than or equal to the degree of the denominator. If the degree of the numerator is larger than the degree of the denominator, let's see what happens. So a linear asymptote that is neither vertical nor horizontal is called a slant or oblique asymptote. For any rational function of this form, P over Q, a slant asymptote occurs when the degree of the numerator is exactly 1 more degree than the degree of the denominator. A graph can cross a slant asymptote, right? So if the degree of the numerator is larger than the degree of the denominator by 1 degree, then we'll have a slant asymptote, right? And the way we find it, once we identify it as a slant asymptote, all we do is like a polynomial long division. And we're going to finish with the equation of a line, and that's going to be the equation of our slant asymptote. Let's see if we can see it. Okay? So notice here, the degree of the numerator is larger than the degree of the denominator by 1 degree. So that means that we should have a slant asymptote, right? So then all we really need to do is polynomial long division. Instead of, I mean, I could do polynomial long division. Since we're dividing by a linear binomial, I'm just going to use synthetic division. All right, let's see if we can get it synthetic division. So ones are 0, right? If we're going to do synthetic division, every power needs to be accounted for. So the first coefficient is a 1. We're missing a term, so we're going to do a placeholder, and then we have our constant term, right? So if we do synthetic division, the first guy comes down. On a diagonal, we multiply. Vertically, we add, we multiply, we add, we finish with the -3, and that's our remainder. Okay. So since we started with the degree 2, this means x plus 1. So it drops down by 1 degree. Okay. So this is equal to x plus 1 minus 3 over x minus 1, right? So then the equation of our slant asymptote is going to come from this guy right here. Okay. So basically our quotient. So then the equation of our slant asymptote is going to be y equals x plus 1, right? So then, like, for instance, if we were to look at the graph of this reciprocal or this rational function and we graph this slant asymptote, you'll see that in the long term, the function is going to get close to this asymptote. That's all they wanted was the equation of the slant asymptote, so I'm gonna stop there. Okay. Now I did polynomial long division here because I could. If I couldn't do, I did synthetic division here because I could, but if I couldn't do synthetic division, then I would have done polynomial long division, and whatever my quotient was, whatever my answer was, that would have been the equation of my slant asymptote. Okay. Okay, so we got y equals x plus 1. I think they did polynomial long division, and you can see the x plus 1 there. Second, now we can see that as the absolute value of x gets very large, see, and it's that same little thing going on. If we let the absolute value of x get large, this guy tends to 0. Because we have a fixed number over a really large number. So the slant asymptote. Same concept as before, just augmented a bit. So therefore, y equals x plus 1 is the slant asymptote. Okay. So that one is fun. I usually leave those as exercises. Okay. Asymptotes of exponential and log functions. So the main thing, if I had to summarize it, exponential functions have a horizontal asymptote, and then you have to track it like through, when you do your transformations or whatever. But exponentials have a horizontal asymptote. Log functions have a vertical asymptote. Let me see. Yeah, that's the main takeaway. All right, that's the main takeaway. Now, there's a few other nuances here, but I feel like they'll come out when you work an example or two. So here we're asked to find the horizontal asymptote. It says asymptotes of this guy. Okay, so the horizontal asymptote occurs is what? X tends to either positive infinity or negative infinity. So let's start by, I just want to focus on this term right here, this guy here. How does this guy behave, right? So I'm just going to pull that off to the side and explore. If we focus on this 25 e to the negative 0.04x, notice it's a negative power, right? So that's going to be the same as 25 over e to the 0.04x, right? So now I'll say something like, let the absolute value of x get very large or tend to infinity, right? So as the absolute value of x tends to infinity, what happens? That denominator goes to infinity. So now we're back to the same thing we had before. We're essentially going to have some fixed number over a really large number. So that means what? It should tend to 0. So this term itself, so as the absolute value of x goes to infinity, it's the same thing as before. That term goes to 0. So then we could say something like f of x, give me just a moment. Let me see, f of x equal to
Bro, it's cold as shit.
1 plus 25 e to the
I left my
negative.
wallet in my car. What up, bro? I left my fucking wallet in my car. That's what we said. Shit.
Yeah, this will be unboxed in just a moment, gentlemen. Keeps coming and going, but it's fun. Yeah, this I usually put all the PDFs on boxes before we leave class. Okay, right. So then we got 200 here. So then we say what? As the absolute value of x goes to infinity, this guy tends to 0. So then what we can do is like 1 plus 0 under 200, which is just 200. Okay. So then the horizontal asymptote should be y equals 200. Okay. So it seems like the takeaway for finding the horizontal asymptote, we're just concerned with how is the function behaving as x either goes to positive infinity or negative infinity. And a lot of it is kind of centered around this concept of something tending to 0 in the long run. So that term essentially just disappears, right? It's a matter of finding which term or terms are behaving this way, right? And so it just happened to be this guy in this case. That term went to 0, and the only thing that was left after that was 200. So it should be y equals 200. So let me see. As x tends to infinity, that term tends to 0. So then the limit as x tends to infinity of f of x is really just 200. And then you could make a similar case for as x tends to negative infinity. Oh, I totally forgot. It's different. Let's look at, well, I think I'm gonna just use this. Let me see. Okay. Now let's see what happens to that term as x, that was as x goes to positive infinity. Let's see what happens as x goes to negative infinity. I'll do this one in green. Okay. So I'll work up here. If we consider this 25 e to the negative 0.04x, and that means 25 over, well, actually, before we do that, if we let the absolute value of x go to negative infinity, right? So we're going to have a double negative. That exponent is actually going to go to a positive. So as the absolute value of x goes to negative infinity, this guy tends to positive infinity, right? So then I'll just kind of keep working here. So then if we consider the limit as x goes to negative infinity, right, of f of x, essentially what we're going to have is 200 over some really large number. So we're still back to a fixed number over a really large number. So then all of this collapses to 0, right? So as x went to positive infinity, it tended towards 200. And then as x goes towards negative infinity, it tends towards 0. Right? So this is, I think this is what's called the logistic growth model, where it's the function kind of starts off behaving like an exponential, and then it tapers and finishes behaving like a logistic, right? And so it's captured here. So as x tends to positive infinity, that term went to 0, and so y tended to 200. That was the first thing that we did. Then we consider as x tends to negative infinity. So then this term now went towards positive infinity, right? Because we had a double negative going on, so it blew up. So then we essentially had 200 over infinity. So again, some fixed number over a really large number is essentially 0. So for positive infinity, we got 200. As x tended towards negative infinity, we got 0, right? So that's why we had a couple of different horizontal asymptotes. So then the line y equals 0 is also a horizontal asymptote of the function. Let's see if we have a picture of this, right? So this is actually a pictorial representation of this graph. As x goes off to the right, it's tending towards this y equals 200, right? It's getting closer and closer to that. As x goes off to the left, the function tends towards 0, right? So this is just a graph, a pictorial representation of what we experienced, right? I like that one. That one was fun. So it did behave different going towards positive infinity versus negative infinity. As usual, if you have questions, feel free to unmute yourself to get my attention and we can talk about it. Looks like we lost at least one person, but it's okay. All right. Otherwise, we're going to power through. Okay. we kind of do need to go into the next section, but I just want to kind of take my time. So whatever we don't finish together, I want to say I have these explanations in my recordings already. Again, I would encourage you to watch those before class, but if we'll do what we can together. That's the only thing that makes me comfortable as far as not rushing, because I know those recordings are there, and it's, I pretty much say the same stuff essentially, same rhythm, delivery, and everything. It's just a recording, so you can go a little bit longer. Okay, so the strategy for sketching graphs. So this is what we talked about when I opened, right, for this section. I want to do at least one curve sketch from scratch, and then I'll probably go into the next section. Let's do a quick recap. Now, I'll let you read through these couple of slides, these few slides on your own. I think I'm gonna just do my own personal summary here, right? I'll do it similar to like what I mentioned before. So to recap, if I wanted to sketch this is a rational function. There are a few steps that I like to do. First, I like to explore my intercepts. As long as they're simple, I'll look for them. I also like to explore any asymptotes. Okay. I usually went another direction from here, but let's go ahead from this point. Let's go ahead and explore let's do our first derivative and second derivative test. So I'll summarize it as derivatives. Derivatives, all right? So first derivative, second derivative. We can also do a test for symmetry. And then I'll say a few additional points. And so each of these marks are loaded, right? There's multiple parts to each of these. We can do a few additional points. And then the final thing is to put all this together so we graph it, right? So if I had to summarize sketching rational functions, I feel like that's about as good a summary as you're gonna get, right? Now, again, each number has multiple parts to it, and I'm actually gonna move this up top just to kind of generate some space. I'll kind of keep it as a reference, but I feel like that's a decent summary of sketching rational functions, at least just based on my experience. And I feel like this should help mitigate some of the anxiety that students tend to have with this topic. So again, you know how to find the intercept of a function, right? You know how to do that. Asymptotes, we kind of introduced some things there today. So, just take your time, get some practice on that. You know how to find derivatives. Sometimes they get a little bit kooky. You just got to accept that, do the best you can with it, and try to explore whatever you can get out of it. Symmetry, if you're not comfortable with that, just look up the definition of what it means for a function to be even versus what a function to be odd, and I'll show you that if we get to it in just a moment. And then a few additional points, we'll talk about that, and then we'll put all this together. You know how to process each of these little individual parts. Now the goal is to try to put them all together in one example. Okay? All right. Buckle up, Buttercup. Let's go. All right. All right. So let's start with the first one. Let's explore intercepts. All right. So just kind of be loose, And I personally like to start with my y-intercept. Let's see. So y-intercept, I feel like oftentimes it's easier than x-intercept. So the y-intercept, all we do is set x to 0. If we set x to 0, we get a y-intercept of what looks like -2. All right. So we say 0, -2. All right. So that's one piece of information. X-intercept. So now x-intercept occurs if we set y equal to 0. So then we're going to have a fraction equal to 0. Now, when is a fraction going to be equal to 0? When the numerator is 0. That's going back to that OK thing and KO thing, right? So this guy is going to be 0 only when the numerator is 0. But notice this numerator doesn't have x, so this numerator will never be 0, so there should be no x-intercept. So it's not going to count the x-intercept, right? So we'll capture that. We'll say x-intercepts, in this case, there should be none. None. Okay? So that was intercepts. Let's explore our asymptotes. So for the x-intercept, we set the numerator to 0. To me, the next logical flow is if you can set the numerator to 0 and get information, then maybe you can set the denominator to 0 and get information. And that should give us information about holes or gaps, vertical asymptotes, things of that nature, right? Okay, it looks like we can factor the denominator. Making up words, the numerator. Denominator and numerator to make the numerator. Making up a new symbol. We'll make it into a T or something in some other kind of operation. Anyway, so we got x squared minus 4, right? Difference is squared. Something squared minus something squared. So I think the values of x that make the denominator 0 are going to be plus or minus 2, and those are indeed vertical asymptotes because they're gonna make like some number over 0, right? It's gonna make 8 over 0 if we plug those in. So a vertical asymptote, right? We got x equals plus or minus 2. So we got 2 vertical asymptotes. So then the next logical flow, if we could talk about vertical asymptotes, maybe we can talk about horizontal asymptotes, right? Horizontal. So I'm just going to go right here. Let's see if we can explore any horizontal asymptotes. So for the horizontal asymptotes, we compare the degree of the numerator to the degree of the denominator, right? If we did a procedure similar to what we did earlier, I want you to notice that the degree of the numerator, which is 0 in this case, is less than the degree of the denominator, which is 2, right? So because the degree of the numerator is less than the degree of the denominator, y equals 0 is going to be our horizontal asymptote. If you let the absolute value of x go to infinity in this case, again, we're going to have some fixed number over a really large number, which is essentially 0, right? So the horizontal asymptote is going to be basically the x-axis or y equals 0. Hopefully this is making sense. Y equals 0, okay? So we have a vertical. I think that if we have a horizontal asymptote, we're not going to have a slant. I don't think those can occur together, all right? So that's chock full of information right there, just on those 2 points alone. So now let's explore our first derivative and our second derivative. I'm not eager for this one, especially because it's in like a quotient form. I think I'd rather do the chain rule. So I'm going to here. So for number 3, let me do it like this, right? And we're on item number 3, derivatives. And see, like this topic is where I really fell in love with mathematics. Like, because it took something that was so abstract with these numbers and it like breathed life into them. So now these numbers have a representation and they take on like this tangible form, right? And now you can make a correlation between the abstract and something that's concrete, right? I don't know. It's just interesting to me. It's not just random and, it's not anything random. It has a meaning. It's a language, right? So this is actually a language course, whether you realize it or not. But let's keep going. So first, I'm going to rewrite my original function. We could work with it in that form, and it would be fine. But I'm just following my prerogative, right? I'm going to rewrite this as this guy, x squared minus 4 to the power of negative 1. Now, I don't know if this is going to make it easier or not. I just have this feeling that it will. So that's why I'm doing it this way. Okay. So we just rewrote the original. So now let's explore the first derivative. Okay. So I think we have to use the chain rule. The power comes down. We subtract 1 from the power. And then we say times the derivative of the inside function, which is just going to be 2x. Okay. Now it looks like we can simplify that some. This is the same as, looks like a negative 16x times this guy. Okay, so that's the first derivative. Now let's go ahead and find the second derivative as well. So if we use this final form that we have, it looks like we have to apply the product rule, along with some other rules, but the main one is the product rule. So let's look at the second derivative. So that's going to be the first, which is this guy, times the derivative of the second. The 2 comes down, subtract 1, times the derivative of the inside function, which is this guy. Okay. So that's the first times the derivative of the second. Then we say plus the second, which is this guy, times the derivative of the first, which is just negative 16. Okay, let's see if we can do some factoring or simplify this down some. They both have that x squared minus 4. Let me rewrite it. So let me think. Give me a moment. It looks like we can factor out a negative 16. Okay, it looks like the common factor. It looks like we can factor out negative 16 times this x squared minus 4 to the, let me think, negative 2. Okay, so if we're factoring that out of both of them, in the first expression, what's left over? We got an x times 2x is 2x squared times, it looks like x squared minus 4 to the power of negative 1, right? When we multiply, we add those powers, so we get a negative 3. 16 times 2. Should that be a 4? I think that's supposed to be a 4. Yeah, right here. Let me check one more time. X, yeah, I think this is a 4 right here. Okay. Let me try to make sure I got my parentheses good. And I think everything is accounted for in that first part. 4x squared, I think everything else is accounted for. And the second one, we factored out a negative 16, x squared minus 4, okay? So it looks like there's a 1 there. Okay. Does that help us any? Let me see. I'm sure we can simplify this down some more. But it doesn't, I'm not seeing it. I think I might leave that as is and kind of keep going. I'm gonna leave it like that for now, right? Now we might be able to simplify that second derivative. I don't want to spend too much time on it. We're gonna let that be. So let's see. So the first derivative, we can use it to find any local max or min. So that's where the derivative is going to go from either, let me think. We got to set it to 0 and solve, or when it's going to be undefined. So I think when x is 0 is going to make it 0. When x is plus or minus 2 is going to make it undefined, right? So those are our critical numbers that we need to test. All right, so if we're working with the first derivative right here, I guess I'll work over here. Okay, here's our positive x. So from the first derivative, it looks like our critical numbers, we have 3 of them. It looks like it's 0 and then plus or minus 2 from the first derivative. Okay. Let's see. It looks like 0 makes the first derivative 0. And these are our candidates for, that makes the first derivative undefined. So these critical numbers break the number line up into 4 regions. We got region A, region B, region C, and region D, right? So then we kind of need to choose test points. If I plug negative 3 into the first derivative, do I get a positive result or a negative result? That's positive. That's positive. If we plug negative 3 into the first derivative, it looks like we finish with a positive result, which implies that the original function is increasing on that region. If we plug a number like negative 1 in region B, plug negative 1 into the first derivative, let me see. The denominator looks like it's negative. The numerator is positive. So ultimately, that's going to be negative, which implies that the original function is decreasing. So then it looks like when x is negative 2, that's our candidate for a local max. Local, I'll call it a relative max. It's like it's going from increasing to decreasing. If we choose a number in region C to test, like when x is 1, into the first derivative. So if we plug 1 in, the denominator is negative, the numerator is negative, double negative is positive. So the first derivative should be positive here, which implies that the original function should be increasing. So this is a relative min, right, minimum value. And then we need to choose a test point in region D to test. So something like 3 into the first derivative. That's going to make the denominator positive, the numerator negative. So a negative divided by positive is negative. So all results here should be negative in the first derivative, which implies that the original function is decreasing, which says that this is what a relative max. Okay. So that was basically applying the first derivative test. And see, we're just about out of time. Well, let's keep going. We're going to keep going. I think we can at least finish this, right? So it looks like we have any vertical asymptotes, plus or minus 2. Let me think. The second derivative, I don't even think I want to fool with it. That would tell us concavity. We would have to find our critical numbers. Let me see. Can I simplify this? Because we would want to set it to, we would essentially want to set it to 0 or find any x that makes the denominator 0. So it looks like when x is either 0 or, I think it's still the same, plus or minus 2. I'm going to go with those. It looks like it's the same critical numbers. So let's plug those critical numbers into the second derivative and see what result we get, like if we get positive or negative. Okay, so I'll put it here, and I'll do it in a different color. I guess I'll do it in green. Just to kind of help it pop up a little bit. So when we plug negative 2 into the second derivative, that's going to make a 0. That's going to be undefined. What about 0? When we plug 0 in, I don't think 0 is a 0 now. But that's a 1. That's going to be positive. That's negative. It looks like the whole thing is going to be negative. So if we plug 0 into the second derivative, I got a negative result, which implies that the original function is concave down there. Okay. We might need to choose something to the left of negative 2, like negative 3. That's going to be positive. That's positive. That's going to be positive. That's positive. Negative. So that's negative times a positive is ultimately negative. So when I chose something left of negative 2, I got a negative result. Concave down. Oh, I hope I'm doing this right. I'm not getting my point of inflection. I feel like I made a mistake there. Let me check. Let me check to the right of 2. If I plug in 3, 9 minus 4, that's going to be positive. That's positive. That's going to be positive. That's going to be positive. Yeah. So I'm getting a positive there. That could be the case. Is there any symmetry? So over here, I got a positive result, which implies concave up. Let me check negative 3 again. That's positive. That's positive. That's positive. That's positive. That forces it to be positive. But then you get a negative there. Yeah, I'm still getting a negative there. When I plug in negative 2, I think it's undefined because we get a 0 in the denominator. Let me check 3 one more time. Positive, 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 positive. Oh, actually, I get a negative there. I'm not getting any points of inflection. I'm getting that they're all negative. It might always be concave down. That could be the case. So I'm actually getting that it's negative. Okay. So there might not be any points of inflection, right? So that could happen. So I'm just going to kind of go with it for now. Okay. Oh, symmetry. Let me do a quick test for symmetry. So for the original function, number 4 for symmetry, so here, let me write this over to the side. A function being even, let's do this in another color. So a function being even, whenever we evaluate f of negative x, we get back to the original. And a function being odd, whenever we evaluate f of negative x, we get a negative times the original. So what we're going to do is evaluate f of negative x and see if either of these cases come out. Okay. So then if we evaluate f of negative x, we're going to get negative x squared minus 4 under 8. If we square a negative, it goes positive. Right? And I think this is the original. So that implies that this function is even. And even is the same as y-axis symmetry. Okay. So we got some information from the first derivative. I feel like maybe that's positive. Let me check 0 again. Because if that's going to be a relative min, it has to be concave up. So this means it has to be a point of inflection, and we're probably just missing it. If I plug 0 in right here, if I plug 0 in, oh, that term is gone. So that's a 1, and that's positive. That's going to be positive. So a negative, it's ultimately going to be a negative times a positive, which is negative. Yeah. Let me think about that. Why is that not working out? I feel like my second derivative might be off. So I'm not going to spend, I don't want to spend too much time on the second derivative. Obviously, I should give myself more space. I'm just trying to get you guys out of here. We did, so with the second derivative, we can put an asterisk in it. Because, I feel like we made a mistake somewhere and I'm just not finding it. But just for the sake of time, I'll come back to it. With the symmetry, though, we got that it is even. So we got that there is y-axis symmetry, which could be the case. Okay. A few additional points. Now, usually I do my few additional points between my vertical asymptotes and any x-intercepts. We got 2 vertical asymptotes. So, I think in our first couple of examples, we just chose a few additional points to kind of plot. So we could do that and then put it all together in a graph. So what I will do, I know that's kind of jammed. Let's copy, come on, or duplicate today.
I have a question.
Let me try to wrap this one up, and then we'll entertain questions because we're almost done. So let me just try to wrap it up. Okay. So I'm going to kind of nix my second derivative dialogue just because I think I made a mistake somewhere and I'm not getting it to work. But I feel like everything else we can use. We got a y-intercept, we got no x-intercept, we got vertical asymptotes, horizontal asymptote, we got y-axis symmetry, and we got our increasing, decreasing. We got from the first derivative, right? So 2, 0, let me see some y values. We'll find that in just a moment. And some symmetry. Okay, I think we got it. So a rough sketch, not too rough. But again, I am trying to get you all out of here. Come on, please. Come on. Oh. There we go. All right, let's go like this. Yep, there we go. I can suppress this for right now. There we go. Okay, so I think maybe on the y-axis, if we go to maybe 20, that might be a good window. And on the x-axis, we need to go to maybe 5 or so. So something like this. So say this was the origin. Let's go like this. We'll let this be our positive x in this direction. We'll let this be our positive y in this direction. Okay. So let me see. If we went 5, 10, 15, that should be enough. 5, 10, 15, like that. 5, 10, 15. Here we can go 1, 2, 3, 4. That should be good. 1, 2, 3, 4. With the origin, this was 1, 2, 3, 4. 1, 2, 3, 4. These are negative. 5, 10, 15, 5, 10, 15. These are negative. So again, just for the sake of time, I'm skipping the second derivative for concavity, but I think everything else is good. I got to go back and think about the second derivative a little bit more. I think I made a mistake somewhere. So our y-intercept is -2. I guess it could be the case. We'll put it here. So that's 2.5. That's going to be about here. So that's like a -2, 0. So we got our y-intercept. We didn't have any x-intercept. We have vertical asymptotes of ±2. So about like here. Let me see. Let's go style. About that thickness, about like that. That's good. Let's copy and paste. So ±2. Okay. All right. So this is x equals 2, x equals -2. Okay. We got a horizontal asymptote of y equals 0. So that's going to be this guy. I guess I can just paste. Come on. Today, please. Please, come on. Paste. What I'm going to do. Something like this. Right? So y equals 0, that's a horizontal asymptote. Okay. So I'm just taking it part by part, right? We got a vertical, horizontal. Now the first derivative, so we had a relative max when, okay, wait a minute. So obviously that can't be it because even though it does go from increasing to decreasing, it's not necessarily a relative max because it makes the original undefined, right? But it looks like we do have that relative min when x is 0, right? So I think that's one that we can plot. So when x is 0, the corresponding, well, I think we got that already, right? But we know that that's a relative min. Let me at least label that. So this is a relative min. Let me see. Is that a min? We plug 0 into the first derivative. That's positive. No, it all goes to 0. Wait a minute. I mean, that's fine. Let me see. Let me kind of keep going. I'll come back to that. 0, -2. I don't think we had anything there. Oh, and then, okay. We're going to come back to the derivatives. We did have some symmetry. So whenever we get a point on the left, we can get a point on the right. So then we should do a few additional points, right? So let's do a few additional points. So for instance, and I think I'm going to just use my calculator. I'm almost done. We're almost there. So I'm going to just do my additional points. I'm just going to use the calculator just for the sake of time. Are you ready to go? Almost. Not bad. Reload and refresh. And so what I'm going to do, in my y equals, we got 8 divided by x squared minus 4. Okay. And then I'm just going to evaluate that function at different values. So for instance, when x is -1, let me see if I hit math as a fraction, 2 2/3. So when x is -1, we get a -2 2/3. -1. Now that one was what, -2? Oh, we had a, let me see something. Yeah, y equals 0. Negative, let me see, when it was 0, we got -2. Let me choose a few additional points. What about the vertical asymptotes? Something is missing. Let me see if I choose like -3, what happens? -1, it's negative. See, it's a little bit further away. It's almost to -3. So the second point that I'm getting a point here, right? Oh. Right here. Like when x is -1, I'm getting, let's go point about here. And if we have that, there should be another one about here. That might be the case. Let's try -1.5. Nope. So -1.5, it should go further down. Yes, it does. Okay. So negative 1.5, we're at negative 4.5. So it's like about here and here. Let's do negative 1.9. Come on. Right? It should be going towards infinity, right? So negative 1.9 is like way down here. All right. And same thing if we did a positive 1.9. So I think we have a sense there. Let's try when x is negative 3. All right, these are my few additional points. So we're at positive 1.6. So negative 3, 1.6 is about here. Okay, that's all I need there. And then if we have that one, that means we also have this one. I think we have all the information, all right? If we keep choosing a few additional points and we put all this together, I think we get an image like this. So now that we have the regions, usually the way it goes is, let me see. So notice we have this point in the upper left is in the upper left region. Generally, the way it goes is we start close to the asymptote, pass through that point, and then we finish close to the asymptote, right? Again, down here, we start close to the asymptote, pass through these points, and then finish close to the asymptote, right? Now I'm going to go back and kind of confirm or deny some concepts that we talked about. Start close to the asymptote, pass through this point, and finish close to the asymptote, right? Now, I just want to glance at something real quick. Our second derivative, concave down. So yeah, okay, I guess that did make sense. But that should be a max. Why is that not working out? I got to check my first derivative. So I think that's where we got kind of a little bit lost at, was our first and second derivative. I think we made a mistake somewhere. But I think this image is good, right? I noticed that it was clear that something wasn't working out with the first and second derivative. Let me see. Like if I chose negative 1, I don't want to do it right now just because we're out of time. Let me do a quick glance. Negative 1, that's going to be negative. That's going to be positive. Positive. That sure is a positive, right? So right here, I'm getting that this guy, and I'll change it to like red, I guess. When I did it just now, that this was positive, which means this is increasing. And I bet if I redo this guy, that's going to change too. For instance, if I do 1, it should be decreasing. If I plug in a 1, that's going to be positive. That's negative, right? So it's ultimately going to be negative. Okay. And I think that this is proper, right? So, because when we look at our graph, we do get that that's a relative max. So that does change this from a min to a max. And these are no longer critical values, right? Because we don't get the sign change. So we only get a relative max at the origin. Well, when x is 0, yeah, when x is 0, right? We only get a relative max when x is 0. The others, it goes from increasing to increasing, right? So it's no extrema there. Okay, so I know we got a little bit, this way kind of towards the end, but that's kind of how it goes. I think this is good though, right? And again, intuitively, I was like, okay, well, we were kind of making a mistake with the first derivative, so I kind of put a pin in it. When it starts to get dicey, just put a pin in it, leave it, come back to it, right? When we did everything else, we did a test for symmetry, so we did get y-axis symmetry. So what that means is that whenever we get a point on the left, we automatically get a point on the right. Then we just plotted a few additional points. Those few additional points told us what region we're in, and then we got an image like this. This is us doing it by hand, okay? Let me see. So they did their intercepts. They got the y-intercept with no x-intercept, right? Asymptotes, I think we had the 2 vertical plus or minus 2. Horizontal was the x-axis, which was y equals 0, so we got that. Now let's look at this derivative. Oh, they didn't do a slant. There's no slant because we have the horizontal. Critical values. Yep, so we got those critical values, 0 and plus or minus 2. Okay, and then the second derivative. Where's the second derivative? Okay, let me see. Okay, they didn't go like into all the details. So I think if we keep working with what we have, we'll get it. Let me see. So the only candidate we have for an extreme was when x was 0, right? Which eventually we got to. I think initially we had something wrong, but eventually we got to the bottom of it. And then we did our first derivative test. Let me see. F double prime does not exist when x is 2 and -2, and neither does f. We consider f equals 0. So they got this. Is this our second derivative? Oh man. So I think we can cancel a lot. Like I think things cancel, but again, I was rushing trying to get through it. So I think if we think about it some more and write it out like on some bigger piece of paper, like more space, we'll see it better. But again, I was just trying to move on. Concavity. Okay, so that would come from the second derivative. We'd have to keep going there. Okay. It's concave up from 2 to infinity, which is what we have. And this is exactly what we got, right? So again, we did the best we could with the derivative. We put a pin in it because we were running out of time. But even without that, we were able to still use the other piece of information along with a few additional points. We did a test for symmetry, a few additional points to put it together, and then we got the same image. That was an adventure. Okay, I know there was a question. We got like literally 1 minute. I know there was a question. I don't know if it got answered or if you still have that same question.
Yes, I have a question. Can you go back to the where you did all the work for the problem for this one?
Come on. Okay.
So I don't understand how you got 4 for the answer, like where the parentheses for x2
in the red
Yes.
circle. Okay.
Yes.
Honestly, when it comes to the first and second derivative, I should just probably put that on a separate sheet of paper and work that by itself, right? We got a little bit lost because we're trying to jam it in the space. So it's easy to lose track. If I had time, I would take this, write it on a blank page, and then work these by itself, right? And that would help with all of that kind of clutter. So that's the first thing. Again, I was just doing this, just trying to wrap it up. So let me do this. Now, when I took my second derivative, I'm going to try to highlight, and I guess I'll do it this way. I'll do them in blue. Things that I noticed that both terms had, right? They both had this -16, right? They both had at least 2 of this guy, right, to the power of -2. This other one had 3, so I know I had to keep one extra. So that's where this guy came from, right? Because, they both had a -16. They both had x squared minus 4 to the -2. So then I was just trying to consolidate whatever was left over. So then I'll do the leftover. I guess I'll do it in orange. So what was left over, we had this -2 and this 2x and one of these guys. So then -2 and this x right here, right? So again, it's hard to see that because it's jammed. So I feel like the colors have to pop. It would be better if I wrote this on a separate page and did it by itself. So now with what's left over, we got x, -2, that binomial, and that 2x. So then that's a -4x squared. Are we missing a negative? No, we captured the negative. We are missing a negative. And that's probably where it was going sideways. Because I think we are missing a negative. We captured this negative right here, but we missed this negative. So then what that would have done, that would have made this negative right here. And that's probably why it wasn't working out. Right? I don't know if that's where you were getting to or not, but I think that's what we were missing, and I think that's why the second derivative wasn't working out. But again, we kind of made that mistake because we're trying to jam it and trying to rush. We should have written it on a separate sheet of paper, nice, big, plenty of space, so we're less likely to make mistakes like that. That was actually a really good call. And I think that's what we were missing. Was that your point or was that your question? You can say yes. Yeah, you can say yeah, just like but that was good, right? So, that was really good. I do need to kind of get on to my next. So if we take it from here, we can fix the whole second derivative discussion and get to the bottom of that. That was good. Okay, let me try to get you guys out of here. So we did that by hand. That was an adventure. We're out of time. So I'm going to have to use my recording for the remainder. But actually, it wasn't really left. So we had one more example. And we were done with this one. Let me just try to do some closing remarks here. No real closing remarks. There is one section that we still need to talk about. So I'm going to have to rely on my recording, and I'm just going to keep the rhythm that's in the syllabus, right? So like today, hang on, let me make a copy of this available. I wanted to get through section 3.4, so I'm going to have to rely on my recording. And we'll probably start with 3.5 on Monday. And I think next week is the week before spring break. All right, gentlemen, I really have to get going, so we're going to go ahead and close the session out here. Share. All right, gentlemen, have a good weekend, and we'll meet back on Monday, same time, same place. Just making a copy of this available. Let's go here. This one, notes. Wait a minute. That's not right. Spring of 24. Traditional calculus notes. Daily. Okay, that's better. Let me see. 3.2. So this is, and I think 3.4. Am I missing 3.4? I think this was 3.4. Yeah. Let me go ahead and make a copy of 3.5 available. I'm so late for this other gentleman. I'm gonna just make a copy of this available. Share. Send it to box. Export. Okay. All right, gentlemen, take care.